Hey guys, we are going to talk about multiple regression and linear regression today. If you understood correlation, this is going to be super easy for you because regression is really just an extension of correlation. In my opinion, it does a couple things. As far as basic statistics is concerned, it helps you predict one variable when you know the other. So in correlation, remember, we're looking at X and Y and looking at the extent to which they are related, right? So in regression, instead of measuring both X and Y, you can measure X, and then knowing a correlation coefficient already, you can plug X into a formula and predict what its Y value would be, right? Its corresponding Y value. The other thing that it helps you do is put that line of best fit in there. So instead of eyeballing it, we actually put a line of best fit in there. Okay, so we have been calling in correlation our variables X and Y. Now in linear regression, we're going to start talking about predictor variables. And we always talk about how correlation is not causation, right? Because we know that, you know, the relationship might be bidirectional. In the marital satisfaction study that we had been talking about and that we're going to continue using for an example, it may very well be that gender role flexibility is leading to marital satisfaction in a wife, and it could very well be that marital satisfaction is leading a man to be more flexible in their gender role. We don't know. But in linear regression, we take a variable, we call it the predictor variable, and then we measure or calculate its complement. So a predictor variable is used to predict a case's score on another variable, okay? So let's look at the marital satisfaction study. Here are the data, and we know there's a positive relationship, right? And we know that the correlation coefficient was 0.76, so it's a strong positive correlation. So, you know, if we try to eyeball the lines of best fit, we can do it in a variety of ways. What statisticians use is a formula called the least squares criterion. It's a way that we plot a line that minimizes the discrepancies between the actual y-scores and the y-scores that we predict. And the differences are shown here. So here is a line according to the least squares criterion. Now the difference between any score and the predicted score is called a residual. And the larger the difference tells you the larger the error in prediction. So how is it that we plot this line of best fit? Well, the formula is pretty easy. It's right here. First of all, the y value that we're going to predict is y prime. And to find that, the formula is b times x plus a, where b is the slope of the regression line, and x is the value for which we want to find the predicted value of y, and a is the y-intercept. So let's first find slope. What is slope? Slope is rise over run. Slope is how steep that regression line is. Essentially, it is for every one change in x, it's how much y changes as well. And to calculate it, we have to look to our correlation information. So we need to know the value of our correlation coefficient, and we also need to know the descriptive data from our correlation. So for x and y, what are the standard deviations? So if we go to our marital satisfaction study, our correlation coefficient was 0.76, the standard deviation for y was 0.86, standard deviation for x was 11.49. We plug that into the formula, and we find that the slope is 0.06. What that means is that for every change in x, for every one change in x, there was a 0.06 change in y for this particular study. So the next thing is the y-intercept, which is A. And the y-intercept is simply where the regression line would pass through the y-intercept. And to find that, again, we have to go to our correlation because we had to find, again, some descriptive information. It's not the standard deviations this time, it's the means of x and y. So the y-intercept is equal to the mean of y, and from that we're going to subtract the product of slope times the mean of x. So we go to our data. The mean of y was 2. Our slope is 0.06. Our mean of x was 25. We work this all out and we get 0.58. So now we know both our y-intercept, A, we know our slope, B, and now we can predict y. So y prime is equal to bx plus a. This is your regression equation. So any predicted value of y is equal to 0.06 times whatever value of x you're trying to predict y from plus 0.58. So what you're doing literally is keeping this number in here, and just plugging in any value of x you want to find y from. So the predicted value of y, if we have a value of 30 for x, would be 2.38. So what this is telling you is if a husband took the marital satisfaction, if the husband took the gender role flexibility instrument, and if he scored a 30, the wife's predicted marital satisfaction would be a 2.38. So let's try this again with a couple of other scores. And let's do this for the lowest score and the highest score in the actual data set. So what is the predicted value of y for a score of 8 on the gender role flexibility instrument? So again, 0.06 times 8 plus 0.58, that gives us 103. And then the predicted value of y for a score of 38 on the gender role flexibility test. You work that out and you get a 2.74. Now the reason why I had you do the lowest and the highest values on the gender role flexibility instrument is because this is how you create the anchors for your regression equation or regression line. So we have 1.03 and 2.74. So we go over here. This is 1.73 on the y-axis. That corresponds to a score of 8. And then we have 2.74 and 38. So high score of 38. And the predicted value is 2.74. So that would be your anchor there. So you have those two anchors, and in there, from there, you create your line of best fit. That's as easy as it is. So what you can also see from this data set is we have the actual values of x, the actual values of y, and now we can calculate all the predicted values of y using this regression equation, right? And then we can look at the residuals. So how far off y and y prime are. And you have the residual scores. You can use these data to calculate the standard deviation of the residual scores. And what that tells you is what's called the standard error of the estimate. So just like standard deviations that we've talked about before, oh, sorry about that. we have standard error of the estimate in regression equations. So what does 0.56 mean? Basically, it's the average residual score, okay? It's the average difference between the actual y-scores and the predicted y-scores. So is it a lot of error? It really depends on the possible ranges of scores. Well, remember, marital satisfaction was on a 4-point scale, 0 to 4. So if we're off by 0.56 points on a 4-point scale, we're roughly off about 14%. So it's not too bad. Not great, but not too bad. Okay. Let me give you, well, I was going to go and talk about multiple regression, but I think I'm going to stop there for now. We'll do another video because we're at 11 minutes already. So that is simple linear regression. Super easy, right? So if you've got questions, you guys know how to reach me, as always, asikorsky@talent.edu. Hope you enjoyed it. Hope it made sense. I'll talk to you soon. There will probably be at least 1 or 2 more videos covering regression. So with that, have a wonderful day.